Welcome to the Walton Pi. Today we're going to go through this problem from complex analysis that is going to involve the Fourier transform. So we are going to be considering the function f of z is equal to 1 over pi times a over a squared plus z squared, where a is bigger than 0. So the first thing we're going to be asked to do is to show that f is going to be in this f sub b class. And so first off, what is that f sub b class? So for this, we are going to remember that we are going to be denoting f sub b. This is equal to the class of all functions which are holomorphic in the strip, which is going to be the set of all z's and the complex numbers, such that the imaginary absolute value of the imaginary part of z is going to be less than b, and we are going to also have it be satisfying the case where the size of f of x plus iy, this is going to be less than or equal to some constant a over 1 plus x squared for all x plus iy in our strip, which is defined above. Alright, so that's what we are going to be trying to prove. So if this is the sort of thing that is helpful for you, please consider liking and subscribing. It really helps me to keep making these videos, as well as signals to me that I should make some more complex analysis videos. Okay, so let's jump right on into this problem. So what we are going to do for this first we are going to prove that our function is going to be holomorphic in that strip, which is not actually that hard. It's pretty straightforward because f has two poles at plus and minus ai, and ai that is going to be outside the strip. So this is going to be holomorphic. So it is holomorphic. We're just going to accept that. And now comes the harder part of part 1. This is going to be, how do we show that it's going to satisfy that? So here's how we are going to go through and do that. We are going to look at what is the size of f of x plus iy. Well, this is going to be equal to a 1 over pi times a over, we have a squared plus x plus iy squared, and all of that is in absolute values. And so what we are going to have is this is equal to, let's see, we got a over pi, because a is bigger than 0, times the modulus of 1 over, we got a squared. Actually, we can rewrite that because it's the modulus of 1 over, it's just 1 over the modulus of the bottom. And let's expand out the x plus iy squared piece. That's going to be plus x squared minus y squared plus 2ixy. And now here's going to be the tricky thing. We need to somehow get this to both drop the y and somehow get just a 1 plus x squared on the bottom. So we're going to say that this is less than or equal to the following. Notice that everything here, all of that is real, and this piece is imaginary. So if we drop the imaginary piece, the modulus is only going to be getting smaller, and since it's in the denominator, that's making this bigger. So that means we get a 1 over, well, a over pi times 1 over, then we are left with this absolute value of a squared plus x squared minus y squared. Okay, so now what are we going to be doing? Well, notice that we know that absolute value of y is less than b, which is less than a. So that means we know for a fact that a squared minus y squared is positive. So that means we actually don't even need the absolute values on the bottom. So that's equal to just a over pi divided by a squared minus y squared plus x squared. Okay. So now here's where we're going to have to do a couple things. We have a couple cases that we're going to have to deal with. So first case, well, actually we don't quite have the cases, but we are going to have to deal with two cases in a second. But what we can do now is we are going to say, well, this is going to be less than or equal to the following. Remember, we are trying to make this bigger, so to make it bigger we can decrease the denominator, and so we can decrease the denominator by making the thing that we are subtracting bigger. So that's going to be less than or equal to a over pi divided by a squared minus b squared plus x squared. Okay, and then what we're going to do is we want to have a 1 over x squared on the bottom, so we're going to divide the top and bottom by a squared minus b squared. So this is equal to a over pi times a squared minus b squared all over a 1 plus x squared over a squared minus b squared. Now here's where we're going to have a couple cases. Well, one more step before the cases. We need to make this bigger. So to make it bigger, we can make the bottom smaller. And to make this bottom smaller, we can make this fraction smaller. And to make that fraction smaller, we can make the denominator bigger. And to make the denominator bigger, we can drop the subtraction. So that means this is less than or equal to a divided by pi a squared minus b squared all over 1 plus x squared over a squared. Here's where we get the two cases. We're finally there. So first case is if a is less than 1. Well, if a is less than 1, what we can do is we have our a over pi a squared minus b squared all over 1 plus x squared over a squared. This is just going to be less than something where we are making the denominator smaller. So if a is smaller than 1, that means to make it the denominator smaller, we are going to not divide by something smaller than 1. So this is less than or equal to a over pi a squared minus b squared all over just 1 plus x squared. So we are going to say that this is equal to our big constant a over 1 plus x squared. Now, our other case is if a is greater than or equal to 1. So if a is greater than or equal to 1, then what we're going to have is we have our a over pi a squared minus b squared all over 1 plus x squared over a squared. This is equal to an a cubed over pi a squared minus b squared all over a squared plus x squared. And to make this bigger, again, we are going to decrease the denominator, so we are going to decrease it by reducing a squared. So that's going to be less than or equal to a cubed over pi a squared minus b squared all over 1 plus x squared, which we are then going to call our a over 1 plus x squared. And there we go. That's how we are able to go through and finish part A of this problem. Okay. Now that we've done part A, let's go back and look at what is part B asking us. So part B is asking us to find f hat. So how are we going to be doing that? So first off, let's look at what is f hat. F hat of x, this is going to be equal to 1 over pi times the integral from negative infinity to infinity of a over a squared plus x squared e to the negative 2 pi I x c dx. So here we're going to need to do a couple different situations. We have basically three cases: if c is bigger than 0, if c is equal to 0, and if c is less than 0. So let's deal with the c is equal to 0. So if c is equal to 0, then this is just the integral from negative infinity to infinity, 1 over pi, a over a squared plus x squared dx, which is just going to be equal to pi over pi, which is 1. Now if you're not sure where that's coming from, that's just coming from making a simple u substitution of saying u equals ax, and then all of this ends up falling out exactly, and you get like an arctangent stuff, and that's where all of that's coming from. So the fun part comes when we are dealing with the cases when c is greater than 0 or when c is less than 0. Now, to show that these are actually the same case, we are going to look at the following. Note that 1 over pi times the integral from negative infinity to infinity of a over a squared plus x squared e to the minus 2 pi I x c dx. This is equal to where we are going to make a substitution of x equals negative x. So that's just going to become a 1 over pi integral from infinity to negative infinity of a over a squared plus negative x squared, that's still x squared, and we have an e to the negative 2 pi I negative x c times negative dx. What we can do is we can take this negative, and then these bounds, and that negative can change the bounds, so then that's equal to a 1 over pi integral from negative infinity to infinity of a over a squared plus x squared. And then this negative sign, we're just going to stick onto the c. So it becomes an e to the negative 2 pi I x negative c dx, which means the integral is the same whether c is positive or c is negative. Both of them are going to work out the same. So we are going to just assume that c is less than 0. So assume c is less than 0. Okay, so here's how we are going to go through the process. We are going to be integrating the function f of z equals e to the negative 2 pi I z c divided by a squared plus z squared. And we're going to be integrating this over the upper semicircular contour that looks like this. So this is r, this is negative r, and we're going to just travel in the standard positive orientation. And now there is only going to be the single pole right here at IA. So we're going to have some sort of pole right there, so we're going to be calculating a residue there and setting everything equal. So let's go over the different pieces that we're going to be doing. So we are going to first integrate over this circular arc, so I'm going to call that c sub r. So the size of the integral over c sub r of f of z dz, this is less than or equal to the length that we integrate, so that's a pi times r, multiplied by the maximum over all the values on there, so all the z equals e to the I thetas, for theta in the interval from 0 to pi, of our function where z is equal to r e to the I theta. So that's going to be all over, we have an a e to 2 pi I r e to the I theta c all over a squared plus z squared, which is going to be less than or equal to, we got a pi r times the little a. The denominator is less than or equal to r squared minus a squared, and we're going to be looking at the maximum over all thetas in 0 to pi of e to the 2 pi r c sine theta, because that is going to be the only part of the top that's actually real. So now that we have that, what's that maximum going to be? Well, here's how we're going to go through and do that. If my whiteboard will slide, there we go. Okay, so here's what we're going to be doing. So we know that since c is less than 0, what we have is the largest that e to the 2 pi r c sine theta can be is going to be when sine of theta equals 0. Because on the entire interval from 0 to pi, sine of theta is positive, r is positive, 2 pi is positive, but c is going to always be negative. So the absolute smallest, or the absolute largest that can be is when c is 0, or not c is 0, but when the top is 0, because otherwise it's a negative number, and e to a negative number is always smaller than e to the 0. So that means that whole thing can just be replaced with a 1. So that means that the integral over our curve of f of z dz, this is going to be less than or equal to pi r a over r squared minus a, which goes to 0 as r goes to infinity. So as we get a bigger and bigger thing, this is going to 0. So that means what we are left with is the integral that we want, the integral from negative infinity to infinity of a over a squared plus x squared, whoops, not x squared, z squared, times e to the negative 2 pi I z c. This is going to be equal to the limit as r goes to infinity of the integral from negative r to r of the same stuff. But this is equal to the same thing as if we were to add the integral over our contour, and this of same stuff. But this stuff, this goes to 0, which means that this whole thing is going to be equal to the residue of our function there. So this is going to all be equal to 2 pi I times the residue at IA of f of z, which is going to be equal to the limit as r, well, the limit of all that stuff above there. So now we just have to calculate what that residue is. Now the residue, that's going to be equal to 2I times, oh whoops, not 2I. Oh no, yes, 2I, because we have the 1 over pi that we were dropping. So when we multiply the pi over, that's where that pi is coming from. So this is going to be equal to 2I pi, oh, it's because we dropped the pi on these terms. So what we have is we really have a 1 over pi is everywhere. So what we're going to be getting is the integral we got is just 2I times the residue. So it's 2I times the residue at IA of f of z. This is going to be equal to 2I times the limit as z approaches IA of z minus IA times a over z minus IA z plus, z plus IA e to the minus 2 pi I z c. So that and that cancel, and then we're able to just plug in AI, and so this is equal to a 2I a over 2AI e to the minus 2 pi I AI c, which is equal to, that stuff all cancels out, and then all that we are left with is an e to the 2 pi a, because the I, and minus all cancel out, 2 pi a c, which is equal to e to the minus 2 pi a absolute value of c, because c was negative, so to make it absolute value, we had to introduce an extra negative. And so that is going to be what the Fourier transform of our function is going to be. I hope this video was helpful. If it was, please let me know, and please like and subscribe. It helps me out quite a bit. I hope to see you all in some other videos, and I hope you have a great rest of your day, and good luck with all of your math.